characterized by E y of t is equal to 100 times cosine of 4 pi times 10 to the 6th t minus 0.1257y.
1257y?
Yes. Close parentheses, and that's in the AZ direction, volts per meter. And they're asking for the wave amplitude, frequency, propagation velocity, wave
What was the first one?
wave amplitude.
All right, well, so they want frequency, they want beta, wavelength, anything else?
Propagation velocity, wavelength,
Is this a
relative per.
lossless media?
Yes, lossless non-magnetic medium.
All right. Well, when you're dealing with something like this, the minute you see an expression, a time domain for the electric field, you can get stuff very quickly. First, the magnitude is simply 100. That's just the coefficient of the cosine. Cosine has a peak value of 1. Follow me on this class? That's a no-brainer in a sense. After that, you get omega. Omega is always going to be the coefficient of t inside the cosine or sine argument. Y'all follow this? This is stable. So we know omega here is 4 pi times 10 to the 6. And that's radians, right, per second. After that, the next thing you always get is beta. And beta is going to be the coefficient of the spatial variable. Now, there are tricks to this, because you could have a wave that has both y and x variation inside that cosine, and I'll deal with that in a bit. But for now, you need the coefficient of the spatial variable. That's beta. Y'all follow me? I'll put omega here. This is beta. So beta here is equal to 0.1257, right? Now, the other thing I'm going to ask the class is, looking at this wave and the expression, which way is it propagating and for what reason?
Propagating y direction.
Say again?
The y direction.
In the y, positive y, right? And the reason you can tell is that's a negative sign right there, right? So it's going in the plus y direction. That's important. You at least establish that. Everybody with me so far? Now, the next thing he asks for is, well, you might as well go and knock them all out at once. From omega, can you get F class by looking at it? What is it? We know omega is 2 pi F, right? Y'all with me? So if you just divide that by 2 pi, you get 2 times 10 to the 6th. And that would be hertz, right? So it got F. Now it's lossless, right? If it's lossless, and the reason you can tell is there's no e to the minus alphas y. Do you follow me? There's no exponential out here that could cause this thing to decay in magnitude. Y'all follow me? Real important. We know it's lossless just by looking. Now, the next thing you ask for, I'm going to try to go through them in a way. He wants the phase velocity. I always recommend you go to the fundamental definition. Do you remember how I got phase velocity back in the day? I did what? I said everything in here is the phase, right? If it's constant, it doesn't change with time. Phase would be constant. So I took a derivative of everything inside there with respect to t. And what you find out is phase velocity was what? Omega over beta. Do y'all remember that? Once we did it, phase velocity is fundamentally omega over beta. In this one, we take a look at it. We've got omega is 4 pi times 10 to the 6th. Beta is 0. I wish you wouldn't do that, but 0.1257. I don't know what that is, but somebody can just tell me. It better not be more than the speed of light, because if it's faster than the speed of light, we've got a fundamental problem. This thing is not accurate in terms of its description of electromagnetic fields propagating.
9.99 times 10 to the 7th.
Or we'll call it 10 to the 8th. So it's about 10 to the 8th. And that would be meters per second. Remember, what's the speed of light in a vacuum? 3 times 10 to the 8th. So we check the box, that makes sense. It's a reasonable field, at least. It can propagate that fast. Now, what else does he want? He wants mu and epsilon, but he says it's non-magnetic, right? If it's non-magnetic, only epsilon relative can affect the phase velocity. Do you all follow me on this? Now, when we're talking about material parameters, and I'm going to just do this one time this way, and I won't the next time, but remember fundamentally when we talk about gamma, it's equal to alpha plus j beta, right? Gamma is the propagation constant. Fundamentally, if you're at a constant frequency, and we are, gamma is equal to the square root of j omega mu times sigma plus j omega epsilon, right? I'm going there for a reason. I want to make sure I stick this, I put this up several times so it'll be ingrained in your memory. That's fundamental. Do you all agree with that? He says it's lossless. Lossless in this case means two things. Alpha is 0. What causes alpha to be 0 is sigma being 0. Do you all see that, class? Everybody follow me on that? And if sigma is 0, then this equation just becomes j beta is equal to, I'd have j omega mu. If sigma is 0, then it's times j omega epsilon, or I have j omega times square root of mu naught epsilon naught, square root of mu relative epsilon relative. I want to make sure you see the logic. If it's lossless, right, sigma is 0. That makes alpha 0, right? If sigma is 0, just look here. You got j omega mu times j omega epsilon, j omega squared, square root of that is j omega. Y'all follow me? Can y'all see it back there, guys? You can? J omega. Now, what is the square root of mu naught epsilon naught? How about we do one thing before that? Y'all see how I can get rid of that j right here? If you can erase something, please do it. I mean, the minute you can reduce the complexity or the amount of stuff on either side, do it. It'll help you see things. All right, now, here's the thing. That's beta. Do we have beta? Yes, right? Just leave beta alone. I have beta over omega here. I'm going to divide both sides by omega. That's equal to square root of mu naught epsilon naught. That's what? 1 over c, the speed of light. And then I say it's non-magnetic, so that means mu relative here is equal to 1, right? So that means this is times the square root of just epsilon relative here. Now I want you to take a look at that. Do you all agree that if I take this equation, divide both sides by beta, by omega, I get this. Do you all agree with that, class? After I do that, I see that I've got square root of mu naught epsilon naught. That is 1 over c, isn't it, class? How many see this right? Y'all follow me? The speed of light c is 1 over the square root of mu naught epsilon naught. That's just by definition. That is the velocity in a vacuum. You all follow me for electromagnetic waves? Now we can get epsilon relative, right? Y'all agree? Epsilon relative is the relative permittivity. I can take beta over omega times c and square it and get epsilon relative. So I can go over here. I'll show you a simpler way. Epsilon relative will be equal to beta over omega times c and then square it. Now I'm doing it that way so you can see the reasoning. I'm going through the whole 9 yards, but I'll show you a shortcut in a second. For our case, what will it be? Well, beta over omega is really what? It's the phase velocity inverted, isn't it? That's omega over beta. So 1 over that would be what? 10 to the minus 8. Y'all see what I'm doing here? I've got omega over beta. I need beta over omega. I just take 1 over this, 10 to the 8th is 10 to the minus 8, right? Put it over here, times c. Well, c is 3 times 10 to the 8th, right? And I got to square that. How many see what happens now? 10 to the minus 8th times 10 to the 8th is 1, right? 3 squared is 9. Epsilon relative for this one is 9. Okay? Is there any other part to that? I think, do they want the wavelength or anything? They do?
Yes, they did want the wavelength.
How do we get wavelength? Not you. Not you and not you. Somebody else. Not you either. Silence a bunch of people. How do we get wavelength, fundamentally? Think about what wavelength means. If we look at the equation over here, when we have something inside here, a wavelength is when the inside changes by 2 pi. Y'all follow me on that? Right? That would be a full period, right? So what changes by 2 pi? The spatial parameters. So when you take beta times the wavelength, you get 2 pi. This is the fundamental thing. So when you take beta times the wavelength, inside that cosine argument, that has to be 2 pi. And that means wavelength is 2 pi over beta. That's fundamental, by the way. It'll always be true. If you look at this, I don't know exactly what that is. It's 2 pi over beta. And beta is 0.1257, isn't it? So what is the wavelength? Anybody?
50 meters.
Say again?
50.
50 meters? Is that what you get?
Yeah.
50 meters? Anything else to this problem? I don't know what else they can ask. We didn't cover power density. Huh? Is that it?
There's part B, which is finding the magnetic field.
Okay, we're gonna cover that today.
Yeah.
That's the lead-in I'm gonna do. I want to make sure this is such a good problem because it's showcasing all the things you can extract just by looking at the mathematics of the wave description. Y'all follow me? Now, I want to tell you one other thing. Generally, anytime you want wavelength in a lossless media, listen to me here. Anytime you want wavelength in a lossless media, you don't need to go through this. Or phase velocity, either one. I'll just show you. So if you want phase velocity, this is only for a lossless medium. And you want phase velocity, what it will, and I'm going to say lossless media and non-magnetic. You simply take C and divide it by the square root of epsilon relative. That will be the phase velocity. Y'all follow me on that? Now that phase velocity we get from omega and beta. We know phase velocity is omega over beta, right? So you can get omega and beta from the mathematical description, if it's given. Follow me? And if you want epsilon relative, well, if omega over beta is given, C is the speed of light, 3 times 10 to the 8, you can surely get the square root of epsilon relative. Y'all follow me? So that's the one I use. The next thing is wavelength. Whenever you want wavelength, well, wavelength, if there was no material, if you were in free space or a vacuum, will be C over F. That's wavelength. Now, we can prove that. I think I did that proof. I did this, I don't know, a lecture or 2 ago. You can just take the fundamental definition of wavelength, right, which is 2 pi over beta, replace beta, if it's lossless, with really omega times square root of mu epsilon, and then let mu and epsilon just be mu naught epsilon naught, and you will get this, I promise you. You get that. With me? Now, if that's wavelength in a vacuum, if you have a lossless or a lossless media that's non-magnetic, you simply divide this by 1 over the square root of epsilon relative, and now you get wavelength 2. And there's a point I'm making here. You see how what epsilon relative really does is slow the rate the wave propagates. Doesn't attenuate, just slows the rate, right? The minute you slow a wave down, you cause the wavelength to shorten, because now for a certain length of time, it can't propagate that far, so it's condensed, it's squeezed in, it's like an accordion. So that's phase velocity. You can get epsilon relative using this equation very easily, and that's wavelength. And that's really it for that. Now, before I continue, was there another question anybody has? Because this is the perfect lead into what I want to talk about today. Okay. Nothing? Y'all with me on this one so far? All right, now the next thing we've got to talk about is H. We've got to talk about, well, if there's an E field, there's got to be an H. As a matter of fact, something I'll just state, I won't prove this yet, but anytime you have propagating electromagnetic energy, you always have an E and an H field, always. One can't occur without the other if it's propagation. And something else, I think I've said this in here, I'm not absolutely sure how I said it when I said it. Did I talk about near field energy, near field effects compared to launched or propagating far field effects yet? All right, I need to say this before I start. If you have just a capacitor and it's charged, it's got an electric field, right, about it. You all with me on this? You charge up the plates of a capacitor, there will be a static electric field about it, between the plates as well as outside, theoretically. Y'all follow me? That electromagnetic energy isn't radiating. It's resident in the atmosphere around that capacitor. And if you put a resistor across that capacitor, all that energy comes back into the capacitor and discharges it, heats the resistor, causes current. Y'all follow me? Now, that energy, the electrostatic energy, is called near field energy. If you have an inductor and you drive a current through that, DC current, then it will create a magnetic field around itself. Y'all agree with that? Right? You can imagine this. That magnetic field has energy. But that energy can be gotten back out. If you put a resistor across that inductor, break the connection that's continuing the current, all that energy in the magnetic field will be dissipated in the resistor. Do y'all follow? Now that's a near field energy. The photons, and you haven't had a lot of this, but when you talk about the individual particles, they're called photons that make up light. Near field energy has something called a virtual photon. Now, I'm not going to go down that road. If you haven't had any kind of advanced physics, a lot of this sounds like it's nuts. But the reason they do that is because they have to find a way of designating photonic energy that is not propagating. It's virtual is the term they use. Frankly, mathematically, it's got a J involved in the description, but don't even worry about that. Now, when you have any kind of charge accelerating, anything, either a charge orbiting like this or a current that has acceleration of charge associated with it, now you launch photons. Those are real photons. They are never linked to the cause of them. They're gone for good. Y'all follow me? They just keep going. When we talk about radiative electromagnetic energy, we're talking about these equations right here, launched photons, really, all right? We don't do it in terms of an individual photon. Anytime you have those, there is always an E and H field that are perpendicular to each other and perpendicular to the direction of propagation. Y'all follow me on that? Now it's real important, at least you have an appreciation for that. The E field doesn't propagate in the direction of the E field. If the E field is oriented this way, it has to propagate in the plane perpendicular to it. All right? The H field also is perpendicular to the direction of propagation. I'll get to this more in a second. So just keep that in mind. And a lot of this stuff, I'll tell you, when you're dealing with some of these effects, you don't fully appreciate them until years later when you all of a sudden have to learn about the fundamental physics of some of this stuff at a much deeper level. And then you say it, but right now you're going to be practicing engineers. You have to know how to make this stuff useful to you and understand. So we do it by, we always solve Maxwell's equations. I said when we had the two, you don't need to write this, just listen to me. We have the two curl equations. We have curl of H is equal to, and I'm going to break this down, go right to the phasor domain. I said it was sigma plus j omega epsilon, right, times E. And then we have curl of E is equal to minus j omega mu times H. Those are the two equations in the phasor domain that describe all electromagnetic energy, period, but really propagating energy in our case. So when I take these things, last time I took two curls of E. Do you remember that? Remember how I did this? I took a curl here. I get curl of E is equal to minus j omega mu curl of H, and I replaced the curl of H with that, and then I solved the equation, and I got this. I got del squared of E minus gamma squared of E equals 0. I'm going to remember that, at least me doing it. You may not remember all the steps. You guys remember that in back or not? All right, I've tried to be clear about this, right? It comes down to that. Then I say we had to make some adjustments. We had to make some assumptions. We had to assume we're a long way from the source, that the E field only is propagating in one direction, and it only has one component, it only has an EX component. Remember that? And I said, we do all that, and we find out that the E field itself will be giving us some EX0 in the plus direction, e to the minus gamma z, plus some EX0 minus times e to the plus gamma z. It's in the AX direction, and that was plane wave propagation. Based on those assumptions, this is a solution of that differential equation. When I break it down, the differential equation for the record is this. So it's a simple homogeneous second order differential equation. All right, now if we're talking about the magnetic field, we're going to do the same thing. It's just I'm going to take two curls of that, and I get curl of H. And you don't need to do this, but just appreciate it. This is going to be sigma plus j omega epsilon times curl of E, right? And I replace that with this, which is going to be minus j omega mu times H. Do y'all follow me? So I do the same thing for the H field that I did for the E field. Are y'all with me in this class? Don't let this scare you. This is a vector identity. It's the gradient divergence of H minus del squared of H. That's equal to, well, you'll notice that this term is gamma squared, right? So it'd be minus gamma squared times H. And remember that gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. So just recall that gamma is something, it's a useful shortcut. It's a shorthand. That way I don't have to keep writing all the time. So now I'm here. Well, now I'm just going to see if anybody can get this. Last time, when it was divergence of E, I said we assume a charge-free region. Do y'all remember that? In this one, you don't need to assume anything. What do you know about the divergence of H? Or better yet, the divergence of B? Always zero. Why is that? You're right. Yeah, there are no magnetic monopoles. Singular magnet. There really are, but only for 10 to the minus 12, 10 to the minus 15 seconds. When you smash things up in these particle accelerators and you're looking for a Nobel Prize, they exist for these people. They don't exist for us, not in the macroscopic world. I thought I'd throw that in there because, you know, I'll just say this. You may not read some of the physical review letters and all this, the latest and greatest stuff. I used to read that all. But one thing you find out is physicists do have a sense of humor. When they name these subatomic particles, quarks, charms, you almost think there's a Lucky Charm in there somewhere coming down. But they have all these goofy names for these subatomic particles. And they're just having fun because they know it sounds nuts, right? This goes away because there are no magnetic charges. I hope the physics department doesn't say that. Anyway, so now I get del squared of H right there minus del squared of just H itself equal, I'm sorry, gamma squared of H is that. That is identical in form to this equation. Y'all follow me on this? Now here's the caveat on this one. And you'll see this in a second. This H field is linked to this E field at a given frequency, and they can't be decoupled. If you have an E field, you have an H field. The H field has to be perpendicular to the E field. As a matter of fact, if the E field is in the X direction, we'll see this shortly, the H field will have some H0 in the positive direction, e to the minus gamma z, plus H0 in the negative direction, e to the plus gamma z, but its orientation will be AY. It will not be in the same direction. Now you'll see that we're going to prove this in a second. Are you with me on this, class? So that's a description of the propagating H field. This was a description of the propagating E field, identical form, only one, that is Y, this is in X direction. And the other thing is we're using, of course, an EX0 and EX0 minus here to designate the E fields. The H field itself, I just put a plus and a minus there. I could put a Y there. You don't need it. Okay, so now, the next thing that happens after this is we've got to find the relationship between E and H in any media. So we do it this way. We take a look at the E field, and I'm going to, for this part, just do only a positive Z propagation. It'll make it easier. So for this, we have an E field, phasor E field, equal to some EX0 in the I'm just going to call it EX0, or better yet, E0, because it's a scalar, e to the minus gamma Z in the AX direction. So I've gotten rid of the negative part of the propagation. Are you with me? Now, I go to this curl equation, curl of E, right here. And I need to show you something about curl of E. When you do curls, in the back of the book, he defines the curl in Cartesian, cylindrical, and spherical coordinates. Y'all with me? I would give you cylindrical and spherical coordinates for the curl. But Cartesian, you should know. When you take a look at the curl of any field quantity, and I'll put in E in general, normally you do it this way with a determinant. You go ahead and put AX, AY, and then AZ across the top. Right below there, you're going to have DDX, and then DDY, and then DDZ here. Y'all with me? Then you put down EX, EY, and EZ. I don't remember if he has this in the back of the book or not, but this is the easiest way to do these things. I can show you for spherical and cylindrical coordinates too how to do it. But determinant's the easiest way. You all had determinants, right? You got linear algebra. Okay. So if I'm doing this for that particular wave, remember it has only an X component. You all see that? So I can make these two 0. So far, so good. Now what happens? Well, this curl becomes what? Curl of E is what? Well, it's AY DDZ of EX. So I have AY DDZ of EX, right? And then I have minus AZ. Now I'm going this way. So it's going to be minus, it would be the AZ direction here. And it would be DDY of EX. I'm just writing it down. Y'all with me? Can you all see this back there? Now, tell me about this one. Take a look at that equation and take a derivative with respect to y. What do you get? Does anything, is it a function of y? Let me ask you that. Do you see a y in there? I don't. It's 0, isn't it? Take a derivative of a constant or something that doesn't vary with the thing you're taking a derivative of, it's 0. So this part goes away, which is nice. Now, I need to take a derivative of EX with respect to Z. Here's my E, right? The X component. Y'all with me on this? What do you notice happening? With respect to Z, I just get a minus gamma out in front, don't I? So I'm going to get, this is going to be minus gamma right here times EX0, or I'll just call it E0 times E to the minus gamma Z. That's what the curl E is for that, that electric field right there. You with me? Now here's why I did it. Because I know this is true. Y'all follow me? And I know this is true. So curl of E right here, follow me now. Write this down. Curl of E here is equal to minus J omega mu times H. Okay? I've got curl E right there, don't I? It's equal to, it's in the AY direction. And it's got minus gamma E0 e to the minus gamma Z. That's equal to minus j omega mu times h. I said it's only propagation in the positive direction, so my h field is this portion. So it's going to be h0, and I better put a plus to indicate these are positive traveling waves, times e to the minus gamma z a y. I want you to look at that for a second and make sure you appreciate the only thing I'm doing is substituting into the curl of E equation the definition of the curl of E, and simply rewriting the H field here in the phasor form. H naught plus, it's propagating wave in the positive direction, positive z. This. Do you all see it, class? With me? Now, I reduce complexity. AY is on both sides, so I get rid of it. What else might I do? Just looking at that. There's one thing I hate. Negative signs. You see how they appear on both sides? I got a negative there, a negative there, right? Get rid of it. You don't need it. Now I've got that, right? What else can I get rid of? Take a look. On both sides, it appears. Yeah, e to the minus gamma z goes away. You all follow me? So get rid of it. And now I have something that links the E field and H field magnitudes. As a matter of fact, this is very important that you write this down. E0 plus over H0 plus for a propagating plane wave is equal to J omega mu divided by gamma. Now that's for a positive traveling wave. I just normally positive traveling wave, like that. That's the way I indicate it. The symbol used for that is eta. And this is called the intrinsic impedance. Of the region. Now I'm going to simplify this, but this is very important. So when I take a look at the ratio of E to H for a propagating plane wave, I have E, in our case it's E0x plus over H0y plus is equal to eta. And eta, now take a look at this, I got J omega mu, and now I'm going to put down the definition of gamma. That's equal to the square root of J omega mu times sigma plus J omega epsilon. Take a good look at that. There's nothing fancy in here. I'm just repeating something. I'm substituting in what the definition of gamma is. Do y'all follow me, class? Gamma is over here. Now, when you look at that, can you see I got J omega mu over square root of J omega mu? That means I really have J omega mu square root. So then I can say that the ratio of E0x to H0y is eta, and eta itself is equal to the square root of J omega mu over sigma plus J omega epsilon. And this is something you have to know. That's called the intrinsic impedance. Y'all heard that before or not? It's identical to the characteristic impedance in its nature of a transmission line. Identical. So if we talk about that in terms of the characteristic impedance, of first free space. If we look at this, by the way, let me do one other thing. These are two positive traveling waves. This is the component, the ratio of E to H if they're positive traveling. Follow me? If they are negative traveling, if I have E0x minus over H0x minus, it becomes minus eta. So there's a negative sign in that ratio. There's a reason I'm putting it down there first. And the way you can find that out, if I went back up here instead of two propagating waves in the positive z direction, if I took the propagation in the minus z direction, you would see, in fact, that would come out. Same magnitude, only has a negative sign in front of it. So, next thing I'm going to do is write something. Yeah.
Is that for the beta right there, is that e to zero x over h0x or h0y?
It's gotta be Y.
Right.
It's E. Now, the reason I'm saying that is this. That means the E field in general, if we're propagating wave in a positive Z direction, or a wave propagating in the Z direction, it's polarized, the E field's polarized in X, then the E field can be expressed as some E naught, write this down, E naught X positive E to the minus gamma Z plus E0 X negative E to the plus gamma Z in the AX direction. And the H field now, instead of putting H naught, what we do is put the ratio, we put down EX0 plus over eta times E to the minus gamma Z minus EX0 minus over eta times E to the plus gamma Z. So that's the reason, see how that's negative there, not positive? Follow me on this, class? These are the two equations that describe E and H that have both forward and reverse propagation for fields propagating in the Z direction, oriented in, the E field's oriented in X, the H field's oriented in Y. Do y'all follow me on this? Please, I know some of this seems like it's overkill, but it's not. You have to have this level of exactness in the way you describe these field phenomena. All right, now, when we talk about that intrinsic impedance right there, it's so important. We know the ratio of E to H, really for, call it the magnitude ratio, for positive Z propagation or positive propagation in general, is square root of J omega mu over sigma plus J omega epsilon, right? Let's take a look at some of the things that you need to know. The really important value is for free space, because that's 99% of everything, maybe 99.99% of everything I deal with is in assuming it's free space or the atmosphere. Very low loss. So if we talk about this value for free space, call it a vacuum. And even in air, generally. Then you get eta is equal to the square root of J omega mu over the square root, or really over sigma 0 over just J omega epsilon, or you get equal to the square root of mu naught over epsilon naught, and that is 120 pi ohms, or about 377 ohms. So when waves are propagating in free space, or in air, pretty much, then if you know the E field, you know the H field. Just divide the E field magnitude by 120 pi, and you got the H field magnitude. Y'all follow me on that? If you're wondering why, take a look at what the value is. If I have eta naught, they call this eta naught, by the way. It's the intrinsic impedance of free space. That's equal to, y'all agree it's equal to the square root of mu naught over epsilon naught, right? Because sigma 0, so the J omegas cancel in there. Y'all follow me? How many see this right here? Animation. All right. So if you do this, do the math on this one. Mu naught is 4 pi times 10 to the minus 7th, right? And epsilon naught is what? Well, you could say it's what? I think Whitworth does this, 36 pi, right? Times 10 to the minus 9. Have you ever seen that before? 1 over 36 pi times 10 to the minus 9. If you do it this way, it becomes pretty clear what happens. I have the square root of, I've got 4 pi times 36 pi, 4 times 36 times pi squared. And then I have 10 to the minus 9th into 10 to the minus 7 is times 100, right? And then you can see what happens here. I get pi, right? And I got 100 square root of that is 10. So that's 120 right there. Yeah. And so it's 120 pi, or about 377 ohms. But that's how you get it. Just put in the values. And that's important to know. Now, anytime you have anything else at all, you always default to the fundamental formula right here if you need eta. All right? Because you don't, if it's got a value of sigma, eta could be anything. You're going to have a real and imaginary component. Are you with me, class? Just remember that. So that's generally how you get eta. And in his book, I'm not using this chapter 5 because it's really kind of a brute force. If you want to really brute force all this, I'll do that for you. But I'm getting to the essence of the reason he's brute forcing it. And this is it. So next, and here's some tricks. They're in chapter 6, but I want to make sure you understand. One of the things everybody wants to do is find out if I got a propagating wave and I know the H field, how do I get the E field? Or a propagating wave and I have the E field, how do I get the H field? These are the equations that are simple, and they simply eliminate the need to solve Maxwell's equations or do curls and stuff like that. And they're two simplifying equations. I'm going to put them here. I think you'll appreciate these. They're in the book, and it's just before the section in chapter 6 on lossy dielectrics. But these are important. So we're talking about propagating waves, and if we have propagating waves, then we can say the H field can be gotten, if I know the E field, by taking 1 over the intrinsic impedance value times a unit vector in the direction of propagation and crossing it with E. Or, if you have H and you want E, E will be gotten by taking minus eta times a unit vector in the direction of propagation crossing to the H field. Now, AP is a unit vector in direction of propagation. So best way to deal with this is for me to give you a problem. And by the way, these are at the bottom of page 327 in the book. So we're gonna do just this one. It's better that I show you something before you leave. So for this one in drill 6.4, it says suppose you have eta of 240 pi ohms, 240 pi ohms. This is on page 328, and they say I have an E field given as 480 pi times cosine of omega t plus 10x AY, it's volts per meter. Find E, here's what they want. They want to find E0, the direction of propagation, H0, and Hx, or the H field of the time domain as a function of xt, and I think they want H phase or here an E phase. So let me go through this with you. This problem showcases a lot of things you probably have questions about. I take one look at this. Well, does it say, by the way, if you're looking in your book on that, can you tell me if that's a lossless, I mean, if it is lossless, but if it's free space, can't be free space. It's lossless. You know how you know it ain't free space? If it was free space, this would be 120 pi. You all follow me? So what we're going to do is we're going to figure out everything about this. So first, the first thing we're gonna do is this. I know this is 240 pi, right? Now when I look at eta, technically it's the square root of j omega mu over sigma plus j omega epsilon, right? If it is lossless, that'll be strict real. If it's lossy, if you get a value of sigma in here, you're gonna have a real and imaginary part. Can you all hear me on that? It is strict real, it's 240 pi. Do you all see that? If it's 240 pi, it means that sigma is 0. Has to be, so I'm going to get rid of it. Now I have this equation, right? You all see how the j omegas cancel? You all with me on this? Got j omega on top here, j omega here. They cancel. I'm left with the square root of mu over epsilon. Now I put in what mu, did they say non-magnetic in here? They must somewhere.
Drill 6-4.
Non-magnetic?
It doesn't say.
Well, he slipped up. Anyway, it does have to be that. But anyway, when I take a look at this, it's going to be the square root of mu naught over epsilon naught times 1 over the square root, or wait a second. Let me go back to that. Square root of mu naught epsilon, mu naught mu relative, my bad, over square root of epsilon naught epsilon relative. So that's 120 pi times square root of mu relative over epsilon relative. Y'all follow me in that class? And he's given that as 240. 240 pi, which means the square root of mu relative over epsilon relative is equal to 240 over 120 is 2, or mu relative over epsilon relative is 4. I don't like that, but that's okay. Next, after that, you see what this is? What does that 10 represent, class? Beta, right? Now, when you look at what gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. Here it's lossless, so sigma 0. If sigma 0, this is just strict real. It means j beta is equal to j omega, and sigma goes away. And then I have square root of mu naught epsilon naught times square root of mu relative epsilon relative. I have beta as 10, so I can get rid of the j's, and I can say 10 over here is equal to omega divided by c times square root of mu relative epsilon relative. Right there. And it doesn't have an omega there. Okay. Well, he's not asking for epsilon and mu though. Okay. So he gives us beta as 10. So for the E field itself, he wants the phasor expression for this. Please watch this. Just give me a minute here. He wants the phasor expression for this. The magnitude is going to be 480 pi. And in a phasor form, it would be e to the minus j 10x in the AY direction. Now take a look at that. I've gone, we don't know what omega is, but we know beta's 10, right? It's propagating in the plus x direction, or sorry, the minus x direction. This should be, that should be this. Should be j 10x. And yeah, he's got that right. That's the E field. What is the direction of propagation now? I'm sorry, I'm trying to wrap this up in a amount of time. Just look at it. Minus x, right? So it's minus x, so this would be minus ax. The H field you can get by simply taking the phasor form of that, 1 over eta, and then times the unit vector in the direction of propagation, which would be minus ax, and cross that into the E field. And then finally, the time domain form is just going to be expanding it with the E, the real part of e to the j omega t times this H field. I'll let you do that part, but I want to take you through that. Now, I'm going to say one other thing about this particular problem. You don't have to find the ratio, you don't have to find mu relative or epsilon relative. He gives it as a ratio, but it's got to be magnetic, and here's why. If it's lossless, anytime eta is greater than 120 pi and it's lossless, it means it's a magnetic material. Mu relative is the only way to get that up there. I'll tell you more next time. Friday quiz on the last two lectures plus tonight's homework, so it'll be related to propagating phenomena. Then I'll give you problems and answers.